we will talk about reductions. By reductions, we mean that we have different distributed service problems or abstractions, and we want to relate these to each other. The question that comes, can one abstraction implement another abstraction? Or is it impossible to implement one abstraction given another abstraction? And this leads to the issue of reducibility and the relationship between different distributed abstractions or problems. We say that x is less or equal y, and these are problems, distributed abstractions, if x can be solved given a solution of y. So here we want to solve x, and this can be solved given a solution of y, which basically says we can implement x given a box that give us the properties of y. And we can read it as x is reducible to y. Informally, this says that x is an easier or as hard problem as y. To study the reducibility relationship, let us first define what is a preorder. And it happens that reducibility is a preorder relation. So a preorder relation, it is a relation, a binary relation, on a set if the elements of the set satisfy the following property. X is less or equal itself, that is reflexivity. Then we have transitivity, which says if x is less or equal y and y is less or equal z, then x is less or equal z. These two properties give us preorder. The difference between preorder relations and partial order relations is that a partial order is a preorder with also an extra property called antisymmetry. Antisymmetry says that if x is less than y and y is less than x, then it implies that we are talking about the same object. So we are talking about the same object, so x is equal to y. For preorder, two different objects, x and y, can be symmetric. It is possible for x to be less than equal to y and y less than equal to x, but we are just referring to two different objects. So i.e. x is not equal to y. Now, reducibility is a preorder. So let us see why. Reducibility satisfies reflexivity because if you want to implement x, if we have an implementation of x, we can implement x. So that's easy. So x can be solved given a solution of x. Reducibility is transitive because if y can be used to implement x and y itself is implemented in terms of z, then of course z can implement x. Say it in words. Since y is reducible to z, we can use the z's implementation to implement y. And then we use the y implementation to implement x. Thus, we have an implementation of x in terms of z. Now, reducibility is not antisymmetric, and thus it is not a partial order, because it is quite conceivable that we have two abstractions, x and y, and we can use y to implement x and x to implement y. In this case, we say that these two problems or abstractions are equivalent. So distinct problems, x and y, can be solved in terms of each other. Let's have some shortcuts here. So this relation says x is equivalent to y, and it is the case if x is reducible to y and y is reducible to x, and we say equivalent to x is equivalent to y. we use this relation, or this notation, to say x is strictly weaker than y, and this means that x can be implemented by y, but the reverse is not true. Y cannot be implemented in terms of x. Or, so that's what we said here. X is reducible to y, but it's not the case that y is reducible to x. So in this case, x is strictly weaker than y, or y is strictly stronger than x. Let's have some examples. First, it is true that diamond P, the eventual failure detector, is reducible to the perfect failure detector in the following sense. The eventual failure detector can be implemented by the perfect detector P. So we just use P as an implementation of diamond P, and we just return P suspicions as the result of diamond P. All traces of P are included in all possible traces of diamond P, therefore P satisfies diamond P's property. In fact, diamond P is strictly weaker than P, so this relation does not hold in the asynchronous system model. So in the asynchronous system model, diamond P is strictly weaker than P. So reductions are common in computability theory to relate certain problems to each other. For example, if we know that x is reducible to y, and we know that x is impossible, then of course we know that y is impossible. So y is impossible to solve. So now we know that diamond P is reducible to P and actually strictly weaker, and some problem Z can be solved with diamond P. Then of course Z can be solved with P. We can draw it this way. You know, P can be used to solve diamond P, and diamond P then can be used to solve Z. Therefore, Z is solvable with P. Well, P is always a stronger abstraction. We can use it to solve a problem if it is solved by diamond P. So the weakest failure detector for a problem. It is often the case that P is used to solve a problem X. So here we have problem X, and here we have P. But P is not very practical because it requires synchrony. And synchrony means that we only can solve the problem in the synchronous system model. So quite often the question becomes, is X practically solvable problem? Which, for example, means, can we solve the problem with diamond P? So sometimes a weaker failure detector than P will not solve a problem X. And this is proved through the reduction relationship. A common proof to show that P is the weakest failure detector for X is to prove that X can solve P. So P is reducible to X, which means X can solve it. So if P is reducible to X, then we know that X is strictly stronger than diamond P. And by strictly stronger than diamond P, it means that we cannot solve the problem using diamond P. And here's a way to think about it. If we assume that we can solve X using diamond P, then by transitivity we know that diamond P can solve P, but that is a contradiction. Therefore we show that P is the weakest failure detector for X.